In example 22.6, I want to give us a chance to be able to see more of the factorial operator just to get more familiar with the way that it works. And on this one it has, for part A, 14 factorial divided by 2 factorial times 12 factorial. So again, the factorial operator is going to have a higher priority over multiplication, division, and adding and subtracting. So unfortunately, and maybe fortunately, I will not be able to call this 24 factorial. That is not going to be permitted. So let's get rid of that. That's not going to be allowed. So the best that I can do is think about what the expansion of these factorials would look like. So for 14 factorial, that's going to be 14 times 13 times 12, and that's going to continue. Now, I'm not going to do the full expansion of this factorial. I'm going to do what I call a partial expansion, and I'm going to stop, and I'm going to write 12 factorial, because 12 factorial would continue with the expansion, but I'm going to stop my expansion of 14 factorial there because I already have a 12 factorial down here in the denominator. So recognizing that I already have all of that same 12 times 11 times 10 times 9 times 8, so on, in the top and the bottom, allows me to be able to cancel all of those factors, which is really just going to leave me with 14 times 13 divided by 2. Since 2 factorial is 2, I can then simplify using the appropriate order of operations, and I get the answer to be 91. So that's what it looks like when you have very specific values applied to the factorial notation here. Now for part B, I want to take a look at a more general statement where there is not a specific value plugged in, yet we're still expected to be able to simplify something like this. This would be analogous to saying something like, say, x squared divided by x. So even though I don't actually have a specific value of x in mind, I should recognize that x squared is x times x, which means I can get factors of x to cancel, which makes the final simplified answer just x. So that way, whenever I do decide what value I want to plug in, I'm able to get to the final answer much more quickly without having to go through extra simplification because we've already done that. So this would be along the same kind of lines. What I find helps with this type of calculation is doing some hypotheticals at first. So here's a hypothetical that I want us to think about. Let's say that we let n be equal to 7, just as an example. So if I let n be equal to 7, then I would have 7 factorial divided by 7 minus 1 factorial, which is going to be 7 factorial divided by 6 factorial. I can do a partial expansion in the numerator and call it 7 times 6 factorial. And I'm doing that partial expansion because I already have a 6 factorial in the denominator, so I can cancel those like factors, and the answer just ends up being 7. So when I plug in 7 to this expression, the answer ends up also being 7. It's very interesting. If I was to do this with, say, I don't know, let's say 42. If I do this again with a different number, let n be equal to 42, then I would end up with 42 factorial over 42 minus 1 factorial, which is 40 factorial over 41 factorial. And again, doing a partial expansion in the numerator will be 42 times 41 factorial. So I can get the 41 factorials to cancel, leaving the answer as just 42. So there's definitely a pattern here that we can see taking place whenever we try some hypothetical specific values. So going back to the general statement where I don't have a specific value to plug in, I'm going to take the numerator and I'm going to do a partial expansion, and I'm going to call it n times n minus 1 factorial. And then the denominator already has an n minus 1 factorial in it, so I can cancel the n minus 1 factorials, leaving me with an answer of just n.